so we're going to look at completing the square with algebra tiles. So I set out x squared plus 6x, and instead of making a rectangle, we have to make a square, right? That's a rectangle, not a square. So to make a square, right, if I go like this, and then the reason it's called completing the square is I literally complete the square. I would have to add in 9 units to the problem. Okay, now I can't add positive 9 without also adding in negative 9. Right, so I add 0 to my problem, and I get this. So I get them all nice and arranged in here. Okay, and so now I still have the value of x squared plus 6x, but what I just did is I rewrote this problem to x plus 3 squared, right? I can literally see the square. X plus 3 on this side, x plus 3 on this side. So x plus 3 minus 9. This has the same value as what I started with. All right, so let's look at the next example. X squared plus 8x plus 3. So I start with this. Here's my plus 3. Okay, so there's my 8x. And so this is where we get the half of b thing. Right, so when I take half of b, but then I have 4, it's going to take 4 squared to fill in. Right, so if I look at the abstract formula, which the abstract formula should come at the end, right? That's very abstract, okay? So when we work through our different representations, we start with the most concrete, which is the tiles. Then I'm going to show you how to use the square also, but this is the most abstract. That should come at the very end. But anyway, we can see the parts of that formula in here with what we're doing with the square. All right, so I would need to add in, let's see, I had 3, and so I would need to fill in with 16. That means I have to add positive 13 and then also negative 13. Okay, so I'm not going to actually take the time to count these out. So imagine I filled this in with positive 13 more to have 16. So I would have x plus 4 squared, but then I had to bring in negative 13. All right, and again, this is equivalent. Okay, so usually when we're completing the square, rather than working with an expression, usually we're working with an equation. All right, one of the main places we do this is when we're working with circles and we have to put the equation into the formula where we can see the center of the circle. So I just did that in pre-calc this semester, and I was horrified to see when I took a survey of hands how many students used algebra tiles to do this in high school, and very few had. My cameraman here, or my camera woman, who is my daughter, she hadn't seen these in high school either. But what do you think about all this?
I think this
stuff?
is awesome. It's a great way to visualize it.
So she loved it when she filmed the last video. She said it made her all excited in a nerdy way about just how cool she thought it was. She hadn't seen this, so I think that it should just be mandatory, like federal law, that you cannot teach completing the square without algebra tiles. So in this example, so usually what we do then is work with, if we're working with an equation, we tell the students, bring the c term over to the other side. Okay, so again, I've got my x squared minus 6x, right? So I split and go half. When I'm ready to start weaning the students off this model, I would use this, right? Where this is my x squared. My 6x gets broken up into 3x and 3x, negative 3x and negative 3x, I should say. And then up here, I'd say, okay, then that's x minus 3, x minus 3. What has to go in here? Okay, so this is like step 2, right? Step 1, the most concrete. Step 2, we're still kind of concrete, but we're starting to actually use x squared x. We're getting a little more abstract. This formula up here is step 3, right? The most abstract. So anyway, this shows that you would want to add 9, and so then students are instructed then if you add 9 to the left-hand side of the equation, we do it to the right-hand side. So I would be adding 9 in on both sides of my equation. I would be completing my square, which would be x minus 3 squared equals 16. And so another way that I could really show what's happening then, if I had this square that was 4 by 4, I could talk to the students about the equality here, right? So this square, so imagine I left that all filled in and this is all filled in, right? But I could say, okay, if these two things are equal, they don't look equal, but if this has to equal this, that would mean that this side, the x minus 3, would have to equal 4, right? And so I'm also illustrating here how I could take the square root of both sides, right? X minus 3 would have to equal 4, therefore x would have to have a value of 7. Okay? Now, since we're talking about equations, it's a perfect segue into our next section on equations. So I made myself a little equations thingy, right, where I've got the two sides and my equal sign. So if I wanted to do this first equation, right, I would lay out, and you could probably do this without really any instruction from me. I'd lay out negative 3x plus 4. This is quite basic. You would be doing this long before you would be doing something like completing the square. So my handout doesn't necessarily go in order of how these would be present in the curriculum. Okay, but you'd go like this, and then, you could also, I often see this as the balance scale approach. You'll see like the balance scales on the equations later in my handout. But anyway, right here I would talk to students about how, I have two choices here. I could either add positive 3 to both sides, right, to make that zero out, or I could add negative 2 to both sides. I think I'm going to go with the positive 3 because that gets rid of the negatives, and it's often a goal to have things be positive rather than negative. Okay, so I'd go like this, and these, of course, are 0 pairs. All right, and then I would tell students, well, how about I add positive, do I have too many here? I'm supposed to have 6. How about I add positive 6 on both sides? Those are all 0 pairs. And now I get 5. And I could go like this if I really want to show how these are equal. 1x would have to equal 2, right? If 5x equals 10, 1x would have to equal 2. So I think that equation solving should be done in this sort of concrete way. Now, let me show you what's going to happen, though. If you teach equation solving in a concrete way, this is what's going to happen when students are solving equations, okay? You're going to give a student an equation like this, and they're going to go like this. Okay? How do we feel about that? All right, do we like that? All right, so let me show another one. Okay, so again, or sorry, that should be a 6x. All right, so they're going to go like this. That doesn't look how it's supposed to, right? That's not how equation solving is supposed to look. So how do we feel about that? I wish we were in class so that you could answer, so I'm actually going to pick on my daughter. Jessica, how do you feel about that?
I don't like it, Mom.
Why don't you like it? Why not?
I don't know, because you're not subtracting from both sides, really.
Well, sure you are, right? Subtract 3x, subtract 3x. Subtract 1,
No,
subtract
Mother, I'm not a math major. Why don't you teach me?
So the reason that probably a lot of you, the first time you see that, you probably don't like it because it's not the way it's supposed to look, right? And so when I taught 7th grade, we used a program called Hands-On Equations, which was a balanced scale mat, and we had dice and we had pawns, and they were blue and red for positives and negatives. And I solved equations that way, and I realized that my students started doing stuff like this on the test. And at first, I didn't like it. All right, at first I said, that's not how equation solving is supposed to look. It's not okay. All right, but, and see, I can't include my daughter now because she doesn't know what I'm talking about when I say conceptual understanding. So if we were in class, I would say to you, did the student who did this show conceptual understanding? Right? And they absolutely did. They probably showed a better conceptual understanding of students who are doing all the steps because, you know, it's supposed to look like this, right? This is what's supposed to happen. Oh, 2x plus 1, right? But did the student in the first example show conceptual understanding? And they absolutely did. All right, and so it did take me a while. When I was teaching this with 7th graders, it took me quite a while before I came to embrace this solution, right? I just felt like it's not the way it's supposed to be, all right? But the student understands just as well when they're doing this, probably even better than the student who's doing this and showing the steps. So I'm encouraging you, again, to kind of think outside the box, right? Think outside of how things are supposed to look and embrace that conceptual understanding can be shown in ways that maybe we think are different than how it's supposed to look.
So you asked me a trick question.
Sorry.